Okay, so we have our quantum numbers that describe where inside of an atom an electron can sit. And what we have here in this image is a picture, or well, I shouldn't say picture, it's a representation of our warehouse, of our atom, where all the different spots where the electron can sit. So each of these little boxes, so the little white squares here, are an orbital. Each one of these things, and you can see there's 3 here, and there's 5 here. Each of those are orbitals, and each of those boxes can hold 2 electrons. So if we have an orbital here, we can put one of them with spin up, and the other one with spin down. And that corresponds to the last quantum number here, the spin quantum number. One of them can be up and the other one can be down. Now, the reason why we have other boxes here other than the orbitals is because these larger boxes represent these shells and subshells. So in the case of this particular graphic, and you might see a few other pictures or representations that look a little bit different than this, but they all follow the same basic trend where you have the shell values, so n equals 1, n equals 2, and 3, and so on, and they are shown with the smaller ones at the bottom, and as you go up, you're going to higher n values, and then you have the subshells inside of those also grouped together. And so we're going to talk about what governs how many subshells you can have, how many orbitals you can have inside of a subshell in this video today. So, our rules for the numbers that are allowed for these quantum numbers are shown right here. Like I mentioned in the last video, our warehouse, where we store our electrons, which again is the atom, it's a little bit weird. It's not like a normal warehouse where you just have, 10 rows of shelves and all the rows are the same size. And now it's our warehouse is a little bit different. There are rules about how many rows we can have, how many shelves can be on a row, and things like that. There are rules that govern where the electrons can sit. And each one of these rules kind of builds on the next one. So for example here, the rules for the principal quantum number, the first quantum number that describes where an electron can sit in an atom, is that the values for that quantum number can be anything from 1 up to infinity. Now in reality, we're never really going to see anything above 7. Theoretically speaking, it could go up to infinity, but realistically, we're never going to see anything higher than 7. So it's going to go from 1 to 7. It cannot be 0. It can be, the lowest value it can be is 1, and it can go up to 7. So that's the first quantum number, the principal quantum number. It can be any of those values. Now, for the second quantum number, the angular momentum quantum number, which is again normally written as a cursive L, that the values that an electron can have for this second quantum number are determined by the value for excuse me, for the principal quantum number. So, if, for example, an electron has n equals 1, the value for L for that electron can only be 0, because the values for L can be anything from 0 up to n minus 1. So if this particular electron is in the first principal shell, then n would be 1. 1 minus 1 is 0. And so the only possible value for this particular electron is 0. Now, if on the other hand you had an electron that was in the second principal shell, then L could be either 0 or 1. Because if it was in the second principal shell, then this n value here wouldn't be 1, it would be 2. and 2 minus 1 is 1. And so you could have either 0 or 1. So the value for L does not have to be n minus 1. It can be any value from 0 up to n minus 1. So the values that are possible for L are determined by the value for n that that given electron has. And the same thing is true for the third quantum number here, the magnetic quantum number. Its possible values are determined by the value for L. So let's say, for example, we had an electron where n was 2 and its L value was 1. In that case, the possible values for m sub L are -1, 0, and +1. Now, it can only actually have one of those numbers, but all three of them are possible. It could have any one of those. It is not possible for it to have an ml value of +2. That's not allowed, because the rules for m sub L are that it can be anything, and I know that looks like a 1. I really should have a different font here. That is anything from -L to +L. So because we said L was 1, that means that our values for ml can be anything from -1 up to +1. Those are the possible values for that number. And then the last one here I've already mentioned before, but it only has two possibilities. No matter what the other numbers are, it can only ever be +0.5 or -0.5, no matter what. So these rules help us explain what we see here in this representation. So if you're in the first principal shell, that very first row in our warehouse, because the rules tell us that the value for the second quantum number is from 0 to n minus 1, and therefore there is only one option, what that tells us is we only have one subshell in this first main shell. And then in addition to that, if we take that a step further, if n is 1, that means L has to be 0. And if L is 0, the value for m sub L, that third quantum number, can be anything from -L to +L. Well, -0 to +0 is just 0. And that is the only possible number that you can have. So, for this first subshell, we have for this first main shell, for the first principal quantum number, which is the first main shell, we only have one possible subshell, and that one subshell only has one orbital available. This m sub L number will tell you how many orbitals are possible inside of that subshell. But if, on the other hand, we weren't in the first shell, let's say we were on the second row of our warehouse, this row is a little bit bigger. In this row, we're allowed to have 2 pallets with boxes on them. So we have the possibility of having L is equal to 0, just like we did down here, but we could also have a second subshell, a second pallet on our row that has L equals to 1. And because this number is larger, that means the number of possible orbitals are also larger. So instead of only being able to have ml equal to 0 for this subshell, we could have ml be -1, 0, or +1. All three of those are possible, and so we have 3 different orbitals that are available for electrons to sit in on this second subshell. And then if we go to the for the second main shell, if we go to the next shell, it has an extra, and one more subshell. And this is going to keep going as we go to n equals 4, n equals 5. We actually add on a subshell. Each time we do that, there's another subshell that is available. And as we go from one subshell to the next, we add 2 orbitals. If you notice here, we started with 1, we added 1 on each side, essentially, of the 0, go up to the next one, we again add 1 on each side, and we'll just keep doing that as well. As we go to more complex, higher energy orbitals, we have more orbitals available to us. So using these rules, we can figure out where in the atom electrons are allowed to sit. So each one of those sets of quantum numbers tells us where an electron is allowed to sit. Now those subshells that we were looking at, so the L is equal to 0, L is equal to 1, L is equal to 2, those actually determine the shape of the orbital. So if you have a subshell where L is equal to 0, which is what we have here, those are going to look like a sphere. They're just going to be a sphere in 3D space. As we go from one to the next, so we go from the first shell to the second shell to the third shell, the shape doesn't change because the L value is staying the same. What's going to change is it's just going to get bigger. It's going to become a larger sphere. For some reason, I'm not entirely sure why. I guess it's a little bit of a shortcut, but people decided to call everything that has an L equals 0 quantum number, to call those S orbitals. So anything that has L equal to 0, we call S. So this is the 1s, it's the L equals 0 subshell in the first principal shell. This is the 2s, 3s, and then so on and so forth. If, on the other hand, we have L is equal to 1, so this is the next subshell, which is only possible after the first one. Remember, the first shell can only have 1 subshell in it. The second shell can have 2. The second row in our warehouse has 2 pallets on it. And so in this one, the shape of the 3 possible orbitals are kind of like dumbbell shapes, where there's 2 different lobes of volume where the electrons can exist. And they don't overlap. They are on opposite, well, not really opposite, but they're on the 3 different Cartesian coordinates. There's which is how we name them, actually. So there's a pz, a px, and a py orbitals. So everything in an atom that has an angular momentum quantum number of 1, so anything where L is equal to 1, we call those p orbitals. Anything with L is equal to 2, which is possible once we get to the third principal shell, we call those d orbitals. So this is the d subshell. And so if we go back here real briefly and just see there, you can see that we said this is the 1s, this is 2s, 3s. So all of these are going to be spherical in shape. We have the 2p and 3p, so those are the dumbbell shapes, and then the 3d is available once we get to that n equals 3 shell. And it has similar kind of dumbbell shape, but it's slightly more complicated. Alright, so then in general, the number of sublevels within a level is equal to n, which we can see back here. So in this level, where n is 1, we have 1 subshell. When n is equal to 2, we have 2 subshells. When n is equal to 3, we have 3 subshells. And that will continue on past that point. Because like I said, n can go up to 7 or so with on the periodic table. The number of orbitals within a subshell, and it says sublevel, but subshell is just, it's the same thing. It's just a slightly different name for the same thing. So the number of orbitals within a sublevel is 2 times L plus 1. So if we go back here and check that again, here in the p orbitals, L is equal to 1. 2 times 1 plus 1 is 3, and that's indeed what we see. We have 3 possible orbitals inside of that sublevel or subshell. And oops, too far. And then last thing here, the number of orbitals in a level is n squared. So for n is equal to 3, that third shell, the total number of orbitals would be 3 squared, or 9. And if we go back and double check that, 1, 2, 3, 4, 5, 6, 7, 8, 9. Yes, indeed, 9 orbitals in that shell. Okay. So we'll do a quick example here. Actually, a couple examples here before we call it for this video. So I would encourage you to go ahead and pause the video now and try to work out these two examples on your own. See if you can solve these, and then come back and we'll work through it together. So this question says, what are the quantum numbers and names, for example 2s, 2p, of the orbitals in the n equals 4 principal level, and how many n equals 4 orbitals exist? Okay, oh, I just did realize that there's one bit of information that you did not have that you would need. So when L is equal to 0, we call that S. When L is equal to 1, that is P. L is 2, that is D. When L is equal to 3, that is F. And from this point forward, so L is equal to 4, that is G. From this point forward, it just follows the alphabet. But we're never going to go even up to G. But just for your own edification, if you're ever quizzed on it, once we get past L is equal to 4 with G, it just goes, you know, well, I guess technically when it gets to F, it goes with the alphabet. But the ones that are not alphabetical are just these here at the beginning. So S, P, D, F, that is the letters that are associated with each of these L values. So what that tells us is that in the n equals 4, because it is the fourth shell, we're going to have 4 subshells. And so we're just going to have those first 4. So we would have 4s, 4p, 4d, and 4f. Those are the 4 possible subshells for the orbitals that exist in there. And then for the second question there, how many n equals 4 orbitals exist? That would just be, because n equals 4, you would square that value, which would be 16, if I remember my times tables. And you can go back and check me if you want to on that. But that should be correct. All right. So the next question here, these sets of quantum numbers are each supposed to specify an orbital. One set, however, is erroneous. Which one and why? So 3 of these are acceptable. One of them, the combination of quantum numbers, is not allowed. It breaks a rule. So if we look at the first one here, A, if n is equal to 3, yeah, just cross that out. If n is equal to 3, is L allowed to be 0? Yes, it is. Because remember, L can be anything from 0 up to n minus 1. So L can always be 0, which then leads us to m sub L being 0. So if L is equal to 0, can mL be 0? And the answer is yes. That's actually the only thing it could be. Because remember, the rule for mL is that mL is anything from negative L up to positive L. So anything in this range, any integer value in that range, mL is allowed to be. But since L in this case is only 0, then the only possible thing it could be is 0, which it is, and so that's fine. So the next one there, if n is equal to 2, is L allowed to be 1? Yes, it is. It is allowed to be 1. That is the largest number it could be. But again, remember, L is allowed to be anything from 0 up to n minus 1. Excuse me. So if n is 2, L can be 0 or 1. So it's okay for this to be 1. So in that case, is ML allowed to be negative 1? And yes, it is, because again, for the same reason here, ML can be anything from negative L up to positive L. So it could be negative 1, 0, or positive 1. So this is perfectly fine. So this one was okay. This one is okay. The third one, if n is equal to 1, can L be equal to 0? Yes. Again, L can always be 0. So if L is 0, can ML be 0? Yes, again, very similar to the first one. So this one is also okay, which then leads us to our final one, which at this point we know has to be wrong, but let's talk about why. So if n is equal to 4, can L be equal to 1? It can, because remember, L can be anything from 0 up to n minus 1. So this is not n minus 1, but that's perfectly fine. It doesn't have to be the largest possible number. In this case, if n is equal to 4, L could be 0, 1, 2, or 3. Any of those are possible. And so it's perfectly fine for L to be 1. However, if L is 1, is ML allowed to be negative 2? The answer to that is no. ML cannot be negative 2. ML is limited by L. So because our L value is only 1, ML, the third quantum number, is only allowed to be negative 1, 0, or positive 1. It is not allowed to go to negative 2. So this one is not acceptable. That is the one that is erroneous, as they say. All right, I hope that makes sense. I know we're getting into some stuff that is definitely a lot more abstract. Chemistry in general is just abstract, but thinking about electrons acting as waves, existing in orbitals with quantum numbers describing them, it is for sure abstract. It's hard to kind of get a grasp on at first, but hopefully with some practice you will get a handle on it. And we will talk a lot more about electrons, electron orbitals, and things of that nature in the videos that are coming up. So I'll see you in the next one.